Hello and welcome to the first session on acids and bases. In this session, we're going to be looking over what an acid and base are. We're going to be looking at some of the basic definitions, and then we're going to move on to how we can do some calculations regarding pH scales, and we're going to consider how pH and acid concentration affects our everyday lives. So in this module, we'll be going over several different topics, the concept of acids and bases, which we'll consider today, the water and the pH scale, equilibrium constants for acids and bases, acid-base properties of salts, predicting the direction of acid-base reactions, types of acid-base reactions, calculations with equilibrium constants, and then finally polyprotic acids and bases. So acids and bases surround us every day. We might not realize it. Sometimes whenever we think about acids and bases, we're concerned about very high strength things like acids burn through tables or in movies, or bases are dangerous or whatever. Some of them are, don't get me wrong, but many of them are important to our everyday lives as flavorings, as cleaning agents. And so you can go to your in your house and you can probably find some of these. Acetic acid, vinegar is used as a flavoring and a preservative. It's common in most cooking cuisines to have acetic acid. Citric acid is also quite widely used. It's also in a lot of fruits. Ascorbic acid, vitamin C, a nutritional supplement, also present in many citrus fruits. Aluminium salts, these are used in baking powder with sodium hydrogen carbonate. So these help as rising agents to make our breads rise. Bases then, so some of them are like sodium hydroxide. So this is oven and drain cleaners. They're also important in lye solutions, which can be used to make traditional soaps, which is why soaps are a little bit basic, but generally the concentration is very low if the soap has been made correctly. Ammonia is used as a household cleaner. It's also used a lot in fertilizer manufacture, although that's not really a household use. Then sodium carbonate used as a water softener or grease remover. Sodium hydrogen carbonate used as a fire extinguisher, a rising agent in cake mixes, such as baking soda. And it can be used as a mild antacid. So if you've got an acidic stomach or you have some reflux or whatever, you can potentially chew on some sodium hydrogen carbonate tablets and you will feel a little bit better. Then sodium phosphate, this is used for a cleaner before painting or wallpapering. So you spread this solution on a wall before you paint or wallpaper it to just remove any of the grease that may stop the paint adhering as you wish. So the earliest acid-base definition is the Arrhenius acid-base definition. And so this is the earliest acid-base definition, which classifies these substances in terms of their behavior in water, because at this point, acids and bases were only really known to exist in aqueous solutions. So under this definition, an acid is a substance with H in its formula that dissociates to yield H3O+. A base is a substance with OH in its formula that dissociates to yield OH-. And so an acid-base neutralization reaction may be like this, where H plus OH- gives water, and the heat of reaction there is about minus 55.9 kilojoules. So a strong and weak acid. So a strong acid is typically one that dissociates into ions in water. So if A is our conjugate base of our acid H, so if we add HA, and this could be hydrochloric acid, HCl, for example, and we add that to water, what we're going to see is we're going to see the formation of the acid, this H3O+ ion. Sometimes you'll see it just written as H+, sometimes H3O+. I prefer H3O+ because that's the real situation in an aqueous solution, plus A-, which would be the conjugate base. But we'll get on to what conjugate bases are later on. So a dilute solution of a strong acid contains no HA molecules, whereas a weak acid dissociates slightly to form ions in water. So in this case, following on from what we learned about equilibria, we're seeing that weak acids don't actually totally dissociate. Whereas strong acids, when you mix them, unless it's incredibly high concentration, so long as they're dissolved in water, they pretty much always dissociate into H3O plus and A minus. The case with a weak acid is different. Only a very small fraction typically actually dissociates into the H3O plus and the A minus, which is why they are typically known as weak acids. Now, the number of strong acids to weak acids known is that there are very few strong acids, and the vast majority of acids are weak acids. If we think about acetic acid, citric acid, ascorbic acid, those are all what are known as weak acids, and they mostly exist in aqueous solution as acetic acid, as citric acid, and so on. And the pHs of those solutions are typically not that low, which means that they're weak acids. So in a dilute solution of a weak acid, most HA molecules are undissociated. So in this case, Kc, which is our equilibrium constant for this reaction, is equal to the products, which are the dissociation products, over the reactants here, which are water, which would be 1, more or less close to 1, and then the HA would be our acid. And this has a very, very, very small value, whereas Kc for a strong acid would be very large. In fact, we wouldn't really need an equilibrium constant in that sense. You can see here that whenever we wrote out our dissociation, we did a left to right arrow, which indicates that the reaction pretty much goes to completion. Whereas for a weak acid, we had our equilibrium arrows showing that it is an equilibrium and that really the equilibrium lies heavily to the left-hand side. So we can see this graphically here. So we have here a strong acid being mixed in water. So we have beforehand, we have the relative concentration of HA. You can see it's 100% HA. Now, after we mix it with water, what we see is that we have 0% HA, and now we have 100% of that HA has been converted into H3O plus and A minus. Now, these have the same height because one HA molecule makes one H3O plus and one A minus. So for a strong acid, there is complete dissociation, and so there will be no HA molecules in solution. And if we were to zoom in on our system here, we would see that as well. We would see there's H3O plus, we would see there's A minus, but we would not see any HA molecules. This is different for weak acids. If, for example, we mix HA, and HA in this case is a weak acid, we can see that beforehand we have 100% HA. Then afterwards we have about 95% HA present in solution, and only about 5% of that HA has been converted into equal moles of H3O plus and A minus. So this is an equilibrium which lies heavily to the reactant side. So HA molecules are present. You can see here we have some A minus. There's an HA there, there's an HA there, there's an HA there. And we have some acid, we have some base, but most HA molecules in this case are going to be undissociated. So if we look here at strong versus weak acids, we have zinc being submerged in two different types of acid, a strong acid on the left and a weak acid on the right. And we can see that the zinc reacts rapidly with the strong acid through the evolution of these bubbles. Then on the right-hand side, we can see the reaction of zinc with the weak acid, where there are not so many bubbles forming. And these bubbles are kind of representative of a reaction between the zinc oxide, in this instance, that coats the zinc metal, and the acid solution. So the acid dissociation constant Ka is equivalent to our equilibrium constant Kc that we saw back in module 2. So HA is going to react with some water, or well, really just be dissolved in some water. And then that's going to give us our H3O plus and our A minus. But if this is a weak acid, we're not going to get that much H3O plus and A minus. And as a result, the solution is not going to be very acidic. So Kc in this instance is analogous to Ka. All the Kc is that it's a special form, or Ka is a special form of Kc, wherein the H2O, since it's effectively a constant because it is the major species, it is the solvent, is present in huge excess, is removed from the equation. So we multiply through by the concentration of H2O. We get that on the left-hand side. So we make this term, Kc times the concentration of H2O, equal to Ka, which is equal to the acid over the dissociated products of that acid. So the value of Ka is going to be an indication of acid strength. So the stronger an acid, the higher the H3O plus concentration, which means the larger the Ka value. Why would we get a larger Ka value? Well, as H3O plus concentration increases, HA concentration consequently decreases, which means if this number gets smaller and this number gets bigger, then overall Ka is going to be larger. So with a weaker acid, we have a lower percent dissociation of HA, leading to a smaller Ka. So Ka values for some monoprotic acids at 25 degrees Celsius. So here is a table of some acids. We have the Ka values. So for strong acids, we have very high Ka values, so 1.1 times 10 to the minus 2. But as those acids get weaker, such as hydrocyanic or hypochlorous acid, we can see that their Ka values are quite small. And this indicates that they have lower acid strength. We see here a range of about 8 orders of magnitude between the weak acids and the strong acids. So we see here red type indicates polarizable proton. All atoms have 0 formal charge. So here, these are ionizable protons. These protons can be removed in a solution or through a reaction. HF even here is present, the hydrofluoric acid. HF is kind of an interesting case. As we'll see later, it's kind of not that strong compared to other group 7 acids, such as hydrochloric acid or hydrobromic acid. But it's pretty strong. But it's less strong than we would expect. Classifying the relative strengths of acids. So strong acids include hydrohalic acids such as HCl, HBr, and HI. And as I mentioned a moment ago, it does not really include HF. HF is a lot weaker than we would assume. And that's really because of the high electronegativity of F, meaning they kind of form a covalent bond. Oxoacids in which the number of O atoms exceeds the number of ionizable protons by 2 or more. So this is going to be nitric acid, sulfuric acid, and hypochlorous acid. So weak acids include hydrohalic acid, HF, acids in which H is not bonded to oxygen or to a halogen, such as HCN, so hydrocyanic acid. Oxoacids in which the number of oxygen atoms equals or exceeds the number of ionizable protons by 1. So here, so we've got so the number of oxygens here is equal or just slightly more than the number of hydrogens. So both of these, so this has got 2 oxygens for every hydrogen. This has got 1 oxygen for every hydrogen. That's a weak acid. Here we've got, if we count the number here, 3 and 1, so that's a difference of 2, 2, and 3. These are strong acids, whereas here the difference is 0 and 1. That's a weak acid. So carboxylic acids, which have the general formula RCOOH, for example, here we have acetic acid or benzoic acid. These are weak acids as well. Carboxylic acids are things that we find quite readily in nature. So classifying the relative strength of bases then. So we've looked at acids, we've kind of considered what are acids and how can we determine which one is strong and which one is not. So here we're going to be classifying the relative strength of bases. And so strong bases include water-soluble compounds containing oxides or hydroxide ions. The cations are usually those of the most active metals, such as M2O or MOH, where M is equal to, M is in group 1 metals. So for example, lithium, sodium, potassium, rubidium, and cesium. And MO in this case, these cases are going to be group 2 metals. So we'll have, like for example, magnesium oxide, or we'll have calcium oxide, strontium oxide, barium oxide, and so on. We could also have calcium hydroxide. We can also have strontium hydroxide and things like that. And then weak bases are really just amines and ammonias. And so ammonia is NH3, that's a weak base. Amines, which have a general formula of like RNH2, R2NH, and R3N, where R is like a an organic group like an alkyl chain or something like that. So really with weak bases, the common structural feature that we see is that there is an N atom with a lone pair. And this is where the electrons are going to come basically in our bases. So our exercise now is to classify each of the following compounds as a strong acid, a weak acid, a strong base, or a weak base. So we have KOH, and so we're asked to sort of determine whether or not that's a strong acid, weak acid, strong base, or weak base. And we can use the rules that we saw on the previous slides. So I'll give you 5 or 10 seconds. You can think through it, and then I'll go through the answer for this one. Then we can move on to the next ones. Okay, so according to the rules that we learned on the previous slides, anything from group 1 or group 2 with hydroxide is going to be a strong base. So yeah, strong base, group 1 metal with a hydroxide. Okay, here we have some form of carboxylic acid. It looks like a butanoic acid. Is this going to be strong base, strong base, weak base, strong acid, weak acid? Again, 5 or 10 seconds. Have a little think. So based on our rules, we know that one of these acids, carboxylic acids especially, they're going to be usually weak acids because they do not dissociate fully in aqueous solutions. So they go. So weak acid, carboxylic acid with the formula RCOOH. So basically, if you ever see the COOH, doesn't matter about the rest of it, really. It just matters about this part. If you see this present, don't let this part really get in your head or confuse you or whatever. Just look for this part. This is the specific moiety that we're interested in. And since it's got that formula, it must be a weak acid. Here we have selenous acid. So is this a weak acid, strong base, or weak base? Well, I called it an acid, so probably know where to start with, but you do need to figure out whether it's strong or weak. Okay, so this is an oxo acid based on the rules that we just learned about. These oxo acids are, their strength is based on the number of oxygens compared to the number of hydrogens. So in this case, this is kind of similar to sulfuric acid. So this selenic acid will have 4 oxygens, 2 hydrogens. That will give a difference of 2, which will mean that we will have a strong acid. So it's an oxo acid, as I said, and there are 2 more hydrogens than protons, which means that it is strong. If the difference is 0 or 1, then it's a weak acid or a weak oxo acid. But if it's 2 or more, then we will have a strong acid. And then finally, we have this one. This is an amine. Again, there's a long chain here. Don't let that get in your head. Only focus on the structure, the structural moiety, which is important. And then think about whether or not it's a strong acid, strong base, or weak base. So 5 or 10 seconds. All right, so we have here an amine. We talked about those previously, and we said that that structural motif, this nitrogen with a lone pair, since this nitrogen is only bonded to this carbon and these 2 hydrogens means it has a lone pair still, means that this is going to be a weak acid, or a weak base even. It's an amine. So autoionization of water. So here we have a lone pair. Water's pretty cool. There's a lot of interesting things that it can do. And one of those is to be amphoteric, which means it can act as an acid or a base. So it does this through what's called the autoionization of water. So this is where one water molecule comes along and takes the proton from another water molecule and makes an acid and a base. Now, there's a very weak concentration here of these, but they still exist. And it's pretty cool how they find out about this property. Like, guess more than 150 years ago now, where they really purified water. They spent a lot of time purifying it and purifying it and purifying it until it was effectively just water, and there was no like dissolved gases or anything in it. And so what they found out was that this really pure water still conducted electricity, although very weakly. And so they found out that this must be due to the autoionization of water. There must be positive and negative ions in the water, but there was nothing else present in the water. There were no salts, there were no dissolved gases or anything present. So it had to be as a result of the water forming the ions. And so this turned out to be true, and it's what's called the autoionization of water. Now it's very weak, but still present. And so water dissociates very slightly into ions in an equilibrium process known as autoionization or self-ionization. Usually you'll see autoionization used more than self-ionization, but it's a term that may be used. So two water molecules, like such as these two, one will use its lone pairs to bind a hydrogen ion on the other water molecule, and then it will abstract it so that we have an H3O plus formed and an OH minus. Now, since we have both of these, they will react again with each other to form this, but this reaction is happening continuously throughout our pure water, and so it's enough to carry charge to have this equation here. So the ion product constant for water is Kw. So Kw is analogous to Kc from our equilibrium constant. Since this is an equilibrium reaction, we can form Kw, and Kw will be really important later on because Kw will allow us to interconvert between acid concentrations and hydroxide concentrations and so on. So Kc for this reaction is going to be H3O plus concentration times OH minus concentration over the square of the H2O concentration. However, the H2O concentration is effectively 1, but we can multiply through by this term and get Kc times the square of the concentration of water and change that into our Kw term. So here we go, multiply through by the concentration of water squared, and then we get Kw, which is going to be equal to the concentration of H3O plus times the concentration of OH minus, which happens to equal 1.0 times 10 to the minus 14 at 25 degrees Celsius. Remember, the temperature can change our equilibrium values. Now, this 1.0 times 10 to the minus 14 at 25 degrees Celsius is a particularly important number, and we need to recall that and remember that as just a kind of thing that exists on a piece of knowledge that we can have. It's very important. So in pure water, the H3O plus concentration is equal to the OH minus concentration, which is equal to the square of this number. So that's going to be equal to 1, or the square root, sorry, of the number 1.0 times 10 to the minus 14, which is going to be equal to 1.0 times 10 to the minus 7. And so both ions are present in all aqueous systems. So the dissociation of pure water, so the auto-dissociation of water proceeds only to a slight extent, but is responsible for a small but measurable presence of H3O plus and OH minus ions. So two water molecules, as we've seen, auto-dissociate to form H3O plus OH minus. This then gives us our Kw, which is a special form of the equilibrium constant for water, and this will be, Kw will be equal to the concentration of H3O plus times the concentration of OH minus, which will be equal to 1.0 times 10 to the minus 14 at 25 degrees Celsius. So pure water contains no other ions than H3O plus and OH minus, and the negative charges must be equal to the positive. And so here, whenever we have a neutral solution, the concentration of H3O plus and OH minus are going to be the same at 10 to the minus 7. Acidic solutions, we have a more or a higher concentration of H3O plus than OH minus. And for a basic solution, we have a higher concentration of OH minus than H3O plus. So here is a nice little GIF of the dissociation of pure water as the water molecule here on the left comes in and grabs the hydrogen ion, and then they form the H3O plus and the OH minus. So acidic and basic, a change in the concentration of H3O plus causes an inverse change in the concentration of OH minus and vice versa. So the higher the H3O plus concentration means the lower of the OH minus concentration. Now, why is this? Well, if we think about it, the more H3O plus we have, the more that will consume the OH minus is present in solution. So if we think about it in terms of this, in an aqueous solution, there are so many OH minus so many OH minus ions, hydroxide ions. So if there are too many hydronium or H3O plus ions, those will react with the OH minus ions, consuming them, so that at the end, all that we're left with is an excess of hydronium ions. The converse is true. So if we have an excess of hydroxide ions, we will end up with lower hydronium ions. And so we can define the terms acidic and basic in terms of the relative concentrations of H3O plus and OH minus ions, such that in an acidic solution, the concentration of H3O plus ions is greater than that of OH minus ions. And in a neutral solution, the concentration of hydronium and hydroxide is equal. And then in a basic solution, the concentration of OH minus is going to be greater than H3O plus. So the relationship between H3O plus and OH minus and the relative acidity of solutions can be seen here. So if we want to know the concentration of either H3O plus or OH minus, we can divide into Kw, Kw being our special water equilibrium constant. If we find out that the concentration of H3O plus is greater than the concentration of OH minus, then we have an acidic solution. If they're the same, we have a neutral solution. And if the hydronium ion concentration is less than the hydroxide ion solution or concentration in solution, we have a basic solution. So how do we go about using these in calculations? Calculations is where we will be predominantly using these things. So calculating the concentration of H3O plus or OH minus in an aqueous solution. So a research chemist adds a measured amount of HCl gas to pure water at 25 degrees Celsius and obtains a solution with H3O plus concentration equal to 3.0 times 10 to the minus 4, and we're asked to calculate the concentration of OH minus. So first of all, we want to know, is the solution going to be neutral, acidic, or basic? This concentration of H3O plus ions is quite high, so it's probably going to be acidic. Remember that it's pure water and it's 25 degrees Celsius, which means that we can, in fact, use our Kw in this calculation. So the solution Kw is equal to this, so it's equal to 1.0 times 10 to the minus 14. So that means that the hydroxide concentration is going to be equal to Kw over the concentration of H3O plus, which is going to be equal to 1.0 times 10 to the minus 14 over the concentration of H3O plus, which is there, which means that the concentration of OH minus is going to be 3.3 times 10 to the minus 11, which is very, very, very small. So this means that the solution is in fact going to be acidic. H3O plus concentration is greater than OH minus concentration. And this means that the solution is going to be acidic. So as we can see, these numbers tend to be very small. So we generally need a good way of sort of calculating these things. So what we use is the pH function. The pH function in an aqueous solution is a way to compare different acidities or basicities on a uniform scale, which is in numbers which are easier for humans to deal with. So instead of like working with 10 to the minus 15, we work with 14, 13, 12, and so on. So in aqueous solution, the concentration of hydronium ions can range from 10 molar to 10 to the minus 15 molar. It is convenient then to express this large range by the logarithmic scale, the pH scale. So pH in this sense is equal to minus log the concentration of H3O plus, and a neutral pH then is concentration of hydronium ions is going to be equal to 10 to the minus 7 molar, which is going to give us a pH of 7. Then for acidic range, it's going to be less than a pH of 7, and for the basic range, we're going to have a pH of greater than 7. So the pH scale then is shown here. So pH is equal to minus log concentration of H3O plus. So that means if we have the concentration of H3O plus, we can find out the pH. Also, if it's done in pure water, we are also able to find it if we know the concentration of OH minus, because Kw is equal to the concentration of H3O plus times the concentration of OH minus. Since we know Kw is always 1.0 times 10 to the minus 14 at 25 degrees Celsius and in pure water, then we can interconvert. And so the pH of a solution indicates its relative acidity. In an acidic solution, the concentration of H3O plus is greater than the concentration of OH minus, which gives us a pH which is going to be less than 7. In a neutral solution, the concentrations are equal, so pH is going to be equal to 7. And in a basic solution, the concentration of OH minus is going to be greater than that of OH plus, or H3O plus. So the pH then is going to be greater than 7. So the higher the pH, the lower the H3O plus concentration, and the less acidic the solution. So the strength of acids and bases. Acids are classified as strong or weak depending on whether their reaction with water to give H3O plus aqueous goes to completion or reaches an equilibrium. So HA plus H2O is in equilibrium with H3O plus A minus, and this has an equilibrium constant of Ka. So the acidity constant Ka, also called the acid dissociation constant or acid ionization constant, is a quantitative measure of the strength of the acid in a given solvent. In this case, water. So the larger the Ka, the stronger the acid. Note, acidity constants are typically written as pKa values, where pKa depends on pKa is equal to the minus log Ka. So weak acids and weak bases exist as conjugate acid-base pairs in an aqueous solution as represented below. HA plus H2O is in equilibrium with H3O plus A minus. And so for a weak acid and a weak base, we have this kind of idea that it doesn't go to complete dissociation. So HA is a weak acid and A minus is the conjugate base of HA. That means that A minus will react with water to form OH minus hydroxide ions plus HA molecules again. So we kind of have this feedback loop where we keep creating the acid, but then the A minus reacts with water to form the hydroxide, which neutralizes this created acid and gives us HA, because whenever we react OH minus with H3O plus, we have that auto dissociation of water equation, and the H3O plus and the OH minus react to give us water. So we end up back at the start with water and the weak acid, undissociated. So weak acids have strong conjugate bases. That's something important and you should hold on to and remember. Weak bases have strong conjugate acids. So the idea that they have strong conjugate bases and acids is what sort of holds them back from actually dissociating properly. And as shown in the above two reactions, if HA is a weak acid, then its conjugate base, A minus, will be a strong base. Similarly, if A minus is a weak base, then its conjugate acid, HA, will be a strong acid. So for example, in hydrochloric acid, which is HCl, we have H, which will dissociate as normal, but the chloride, the Cl minus, is a weak base. This means that it's easy for it to dissociate, and it won't likely react back to give us the original HCl. And that's why we have this very high rate of dissociation. So here are some Ka values at 25 degrees Celsius, how those correspond to pKa values. Remember that pKa is equal to minus log Ka. And so a low pKa value corresponds to a high Ka value. So here we have a small pKa value. So this is going to be a pretty high Ka value. And this high Ka value means that we have a strong acid. Which hydrogen sulfate ion, sulfuric acid is a strong acid. Nitrous acid, acetic acid then has a high pKa value. You can see here the various species. So you can see here phenol is basically a base at this point. So pH, pOH, and pKa, or pKw, sorry. So what is the interrelationship between all of these things? Well, actually, the beauty of it is, thanks to Kw, if we're doing this in pure water at 25 degrees Celsius, we're able to interconvert between all of these things. The reason it's specified at 25 degrees Celsius, remember it from our equilibrium lectures, is that changes in temperature can affect the value of Kw, or the equilibrium constant. So pH is equal to minus log the concentration of H3O plus, and POH is similar to pH in that the sense that POH is equal to minus log concentration of OH minus. So pH plus POH is equal to pKw, and so for any aqueous solution at any temperature. But the value of pKw will change. So pKw is equal to pH plus POH, which is equal to 14.00 at 25 degrees Celsius. So since Kw is a constant, the values of pH, POH, H3O plus concentration, and OH minus concentration are all interrelated. This means that in any given problem, we're able to utilize any one of those or a combination of them to get other values. So if the hydronium ion concentration increases, the hydroxide concentration decreases, and vice versa. If pH increases, POH decreases, and vice versa. And so here is an example of how we can go about using that. So here we're asked, we're going to be calculating the hydronium ion concentration, we're going to be calculating pH, we're going to be calculating hydroxide ion concentration and POH for strong acids and bases. So we're asked to calculate H3O plus pH, hydroxide concentration, and POH for each solution at 25 degrees Celsius. So we're given 0.30 molar nitric acid used for etching copper metal, and then in part B, we're given 0.0042 molar calcium hydroxide used in leather tanning to remove hair from hides. Okay, so we're going to have to calculate these things for these two solutions. Here is how we would do it for the first one. So we're calculating the values that we're asked for 0.30 molar HNO3, this is nitric acid. So the concentration of H3O plus is going to be 0.30 molar. That's because nitric acid is a strong acid. How do I know it's a strong acid? Well, if we go back to our rules that we saw at the start, we'll discover that this is an oxo acid, meaning that it has oxygens, and the number of oxygens is 3. The number of hydrogens is 1. This gives a difference of 2. And we were told that 2 or more oxygen to hydrogen difference means that it is going to be a strong acid. So we can then directly convert this 0.30 molar HNO3 to a hydronium concentration of 0.30 molar, because when this dissociates in water, it will dissociate to give H plus, which is hydronium H3O plus, because they react with water, like in the auto-dissociation of water, and a nitric ion. So the nitric ion is NO3. So this NO3 minus just is a weak conjugate base, and so it doesn't really react with water to give the acid again. So we can find pH pretty easily. So pH is going to be equal to minus log the concentration of H3O plus, or the hydronium ion concentration, which is going to be equal to minus log 0.30, which means that we have a pH of 0.52. Then to find the hydroxide concentration, we need to use our Kw. So that means Kw over the hydronium ion concentration. So it's going to be equal to 1.0 times 10 to the minus 14 over 0.30 molar, which will give us 3.3 times 10 to the minus 14 molar as our hydroxide concentration. Then we can plug that into our POH calculation. So POH is going to be equal to minus log to the base 10, the hydroxide concentration. And so that's going to be equal to minus log 3.3 times 10 to the minus 14, which will give us a POH of 13.48, indicating we have a very acidic solution. So then calculating the values of 0.0, or calculating the values for 0.0042 molar calcium hydroxide. So this is a group 2 hydroxide, which means it's going to be a strong base, which means it's going to dissociate well in water. It's what's called a strong electrolyte, which means it pretty much totally dissociates. So calcium hydroxide is a strong electrolyte. Calcium hydroxide, when dissolved in water, will give our calcium 2+ ions plus 2 hydroxide ions, which will also be in water. So our hydronium ion, or sorry, our hydroxide ion concentration is 2 times the concentration of calcium hydroxide, which is equal to 0.0084 molar. Why is it 2 times? Well, for every calcium hydroxide that dissolves in water, it dissociates and gives us 2 moles of hydroxide. So 1 mole of calcium hydroxide contains 2 moles of hydroxide ions. So the POH then is equal to minus log the concentration of hydroxide. So that's going to be equal to minus log 0.0084. So that will give us a POH of 2.08, a fairly basic solution. Then to find the hydronium ion concentration, we do the same as what we did in part A, only in reverse. This time it's going to be equal to Kw over the concentration of hydroxide ions. And so that's going to be equal to 1.0 times 10 to the minus 14 divided by 0.0084 molar, which will give us a value of 1.2 times 10 to the minus 12 molar. So pH is then equal to minus log hydronium ion concentration. And so that's going to be equal to minus the log of this hydronium ion concentration that we just calculated, which will give us a value of 11.92, which will be a fairly basic solution. Now, one thing you might have noticed here is that if I add these two values together, I will get the pKw value of 14, because remember that pKw is equal to pH plus pOH. And so you get the same thing here, 13.48 plus 0.52 will give us a value of 14. And it just confirms that interrelatability of those equations that we learned earlier. So how do we go about measuring these things in reality? Well, we can use things like pH sticks, pieces of paper which have little molecules on them, which will change color based on the concentration of hydroxide or hydronium ions, and can then be used to determine pH. Or we can use a pH meter here, which is based on the conductivity of the solution, because remember, if we've got ions, we can conduct electricity. So the Brønsted-Lowry acid-base definition: an acid is a proton donor, and any species that donates a proton, H plus ion, is going to be an acid. So a Brønsted-Lowry acid must contain H in its formula, and that H must be what's called acidic or ionizable. So a base is a proton acceptor. And so this is any species that accepts an H plus ion. And so therefore a base must contain a lone pair of electrons to bond to H plus, or it has to have a negative charge or a lone pair of electrons. Generally, it's a lone pair of electrons. Now, this is quite powerful because previously we've been working under the assumption that all acids and bases existed in aqueous solution. That was the Arrhenius acid-base definition. But now we're broadening that definition somewhat, and we're now only concerned about the presence of protons or not. And so this means that we now have the ability to have acids and bases outside of aqueous solution. We've got no mention of hydroxide anymore, and we have no mention of a proton ion in water. So an acid-base reaction is called a proton transfer process. So the proton is transferred from an acid to a base. So in the Brønsted-Lowry acid and base definition, a Brønsted-Lowry acid is a substance that can donate a hydrogen ion, and a Brønsted-Lowry base is a substance that can accept a hydrogen ion. So in this reaction, we have HCl plus NH3. So HCl is hydrochloric acid. NH3 is ammonia. Ammonia is a weak base. HCl is a strong acid. And these form an equilibrium wherein we can form ammonium, which is NH4 plus. It's gained a proton, H plus proton, which gives us this NH4 plus, this ammonium, plus this chloride. Chloride is the weak conjugate base of the strong acid HCl. So we have an acid, we have a base, we have a conjugate acid, and we have a conjugate base. So water can act as a base or an acid. This is called amphoteric behavior. So water, remember from the auto-dissociation or autoionization that we discovered earlier, two water molecules can auto-dissociate to give H3O plus and OH minus. So H2O is the conjugate acid of OH minus and the conjugate base of H3O plus. H3O plus is the conjugate acid, OH minus, the conjugate base of H2O. So the Brønsted-Lowry definition includes also acid-base reactions in the gas phase or in solvents other than water. So for example, liquid ammonia. So this gives us two ammonias can react in a similar way to water, where we can have auto-dissociation of ammonia to give ammonium and amide. So note, in any solvent, the direction of the reaction is always such that the products are weaker acids or bases than the reactants. We saw that in the case of the dissociation of HCl, where in the HCl, the chloride was a weaker base was produced. So solvent dissociation theory, so the Brønsted-Lowry theory, is limited to proton transfer reactions and mostly aqueous systems. I mean, it's still mostly aqueous systems that we'll be dealing with, but it broadened the definition sufficiently that it meant that we could do it in other systems. So the Brønsted-Lowry theory is limited to proton transfer reactions and mostly aqueous systems. Therefore, aprotic non-aqueous systems require a different definition of acid and base. So the cation resulting from the auto-dissociation of a solvent is the acid, and the anion resulting from the auto-dissociation of the solvent is the base. So here we have two waters auto-dissociating to give the hydronium ion and the hydroxide ion. So the hydronium ion is the cation resulting from the auto-dissociation of the solvent, and therefore it is the acid. And the anion resulting from the auto-dissociation of the solvent is the base. So this is the hydroxide is the anion, and so it must be the base. Acid, base. Other solvent dissociation equilibria. So we have here for this acetic acid, or sorry, not acetic acid, ethanol. Ethanol can auto-dissociate to give the proton and give the, the cation and the anion. That should only be 1 plus. And then it should be C2H5OH2 plus. Here we have ammonia dissociating to give ammonium plus amide. So amide is the base because it is the anion resulting from the auto-dissociation, and ammonium is the acid because it is the cation resulting from the auto-dissociation. So the properties of solvents. So here we have some protic and aprotic solvents. We have how their boiling points change and how their pK ions are, and the different acids and base cations and anions. And so here these can be solvents. Sulfuric acid can in fact be a solvent, depends on what reaction you're doing, but there are many instances where sulfuric acid, especially in a traditional organic chemistry, is used as a solvent. So ammonia is here, sulfuric acid is here. You can see some of their pK ions. So we can see that ammonia doesn't really like to dissociate that much. Sulfuric acid dissociates pretty well. You see water, its pKw is 14. We already knew that. So here are some aprotic solvents. They obviously don't dissociate at all. So like dinitrogen tetroxide, sulfur dioxide, pyridine, these things don't dissociate. So Brønsted-Lowry acid-base reactions. So we have here HCl reacting with water. So HCl is the acid, it is the proton donor, and water is the base, it is the proton acceptor. So what we have here is that the proton is transferred from the water to, or sorry, from the acid to the water. So then this leaves us with chloride plus our hydronium. So the lone pair binds the H plus. In this case here, we have a Brønsted-Lowry base reaction where we have a ammonia plus water gives ammonium plus hydroxide. So what we have here going on is this idea that the ammonium reacts with the water to give, or sorry, the ammonia reacts with the water to give ammonium plus hydroxide. So the lone pair in this case binds the proton and forms the ammonium. So conjugate acid-base pair. So in the forward reaction, here we have H2S, hydrogen sulfide plus ammonia gives us this HS minus plus this NH4 plus. So that's the forward reaction. So NH3 accepts a proton to form NH4 plus. Then H2S donates a proton to form HS minus. And in the reverse reaction, we have ammonium donates a proton to form ammonia. And then we have this HS minus which is going to accept a proton to form H2S again. So here's the reaction, that's the equilibrium. So H2S and HS minus are conjugate acid base pairs. HS minus is the conjugate base of the acid H2S. So NH3 and NH4 plus are conjugate acid base pairs. So NH4 plus is the conjugate acid of the base NH3. And then a Brønsted-Lowry acid-base reaction occurs when an acid and a base react to form their conjugate base and conjugate acid respectively. So we have acid 1 and base 2 gives base 1 and acid 2. So on the left-hand side, species 1 is an acid and species 2 is a base. On the right-hand side, species 1 is the base and species 2 is the acid. So here are a few different examples of some conjugate acid-base pairs, some conjugate acid-base reactions. So we can have a look here, for example, at the first one. So that's going to be hydrofluoric acid plus water will give F minus fluoride plus hydronium ions. So the hydronium ions is the acid, which has got a conjugate base, which is water. And then the F minus, the fluoride, is the conjugate base of HF, the acid. And so you can see some others here, some other conjugate acid-base pairs. So here we have sulfuric acid. This is an acid, so its conjugate base then is the HSO4 minus. And so this can accept a proton to form the acid again. And then this one here, this N2H5 plus, it can in fact accept a proton to form the acid here, which can then donate a proton to form the base again. So we're going to be asked to identify the conjugate acid-base pairs in the following reactions. So the following reactions are important environmental processes, and we're asked to identify the conjugate acid-base pairs. So here we have H2PO4 minus. So this is a phosphoric acid that has been deprotonated. It starts off as H3PO4 as the phosphoric acid. And so this is going to be reacting with this carbonate. This forms hydrogen phosphate, and then this forms hydrogen carbonate. So where is the conjugate acid? Where is the conjugate base of each one of these? So obviously this is a pair with this, but which one is the acid and which one is the base? So this would be the base because it has the lower charge and it can accept a proton to form this. And this is the acid because it can donate a proton to form this. So this is the conjugate base and this is the conjugate acid. And then this is paired with this one. And so this one has accepted a proton. So if it has accepted a proton, then it must be the conjugate acid. So this acid, this one can then donate the proton to form this, which is the conjugate base. So there we go. And then here at the bottom, we have water and we have SO3 2 minus, and then we have hydroxide and we have H2SO3 minus. So this has accepted a proton. So this must be the base, and then this must be the acid because it can donate a proton to form this again. This is the base because it is hydroxide and it can accept a proton to form the acid, which can donate a proton to form the base, like so. So the net direction of a reaction. So the net direction of an acid-base reaction depends on the relative strength of the acids and bases involved. So the reaction will always proceed to form the weaker acid or base. So a reaction will favor the formation of the weaker acid and base. So if we have hydrogen sulfide and ammonia reacting to form HS minus and ammonium, then we have a stronger acid, a stronger base reacting to give a weaker acid and a weaker base. Hydronium is a weak base or a weak acid. So this reaction formation favors the formation of the products. So strengths of conjugate acid-base pairs. The stronger the acid is, the weaker its conjugate base. So when an acid reacts with a base that is farther down the list, the reaction proceeds to the right. Kc is greater than 1. So here we have the acid and the conjugate acids and bases of two different species. So we have HCl minus, we have chloride. Chloride has got a negligible strength, so it's a very weak base, which means that HCl is a strong acid. If we go down here, we can see that hydroxide is weakly acidic, which means that oxide ions are going to be strong bases because the direction of the reaction will almost always proceed from oxides to hydroxides, things like that. A hydroxide will almost always proceed from hydroxide to water, for example, because the water is a weaker acid than the hydroxide is a base. So the hydroxide base is strong. So the formation of water is a weak acid. So that means that direction of the reaction is favored. So we're asked to predict the net direction of an acid-base reaction. So predict the net direction and whether Kc is greater or less than 1 for each of the following reactions. Assume equal initial concentrations of all species. So here is reaction 1, here is reaction 2. We can use our previous table to help us with these problems. And we can use the previous table to kind of tell us which one is going to proceed in which direction. So we see all these reactions earlier, they're the same reactions. So we know that H2PO4 minus is the conjugate acid of this, the conjugate base. This is the conjugate base of this, the conjugate acid. So we want to know which one is stronger than the other. So we know that we know which direction is going to be favored. So we can go back to our table and we can see that if we look at H2PO4 minus, H2PO4 minus is here, and then we're forming this. So this is a weak base, and this is a weak acid, albeit this is a stronger base than this. So the reaction is going to probably favor this formation. So let's check in with our carbonate. So here is a carbonate, and then this is the hydrogen carbonate. So most likely this one will be, this is a stronger base than this is an acid. So that means that the reaction is probably going to favor the formation of the hydrogen carbonate. So most likely the reaction will favor the production of these two species as compared to these two. Then you can do the same process for this. So water plus this sulfate is going to be reacting to give hydroxide and hydrogen sulfate. We want to know which one is going to be the preferred side of the reaction. So here, the plan is that we identify the conjugate acid-base pairs and consult a figure on the previous slide to see which acid and base are stronger. The reaction favors the formation of the weaker acid and base. So in the case of this setup here, we have water, and then it wants to form hydroxide, so we can check with water and hydroxide. So whereas water and whereas hydroxide. So hydroxide is a strong base, so the formation of water will be preferred. And the other one was this SO3 minus with the HSO3 minus. So this is a weak base, but it's kind of on the strong side, whereas this is a weak acid, but it's kind of on the weak side. So it's going to favor the formation of this one. So we have a favorable formation of this, but we have an unfavorable formation of this. This is the strongest species present. So most likely it's going to lie on this side. So stronger acid, stronger base, weaker acid, weaker base. The net direction of this reaction is to the right. So Kc is greater than 1. And then we have here weaker acid, weaker base, stronger acid, stronger base. So the net direction is to the left. So Kc is going to be less than 1. So we used our table and we accurately predicted which side would be the net direction of the reaction. So don't always think that the reaction is always left or right. It's not always left or right. We have to inquire about the species and see which ones are going to be more or less reactive. Which one's going to be the stronger acid, which one's going to be the stronger base. In these types of reactions, what we typically see is the formation of the weaker acid or base is favored. So thank you for watching that session. Tune in for the next session.